member as a member of LIGO to the first detections of gravitational waves. I think that's a great thing to have in your PhD. And she's actually also led several of the detection and cosmology focused papers of LIGO. In her other work, she particularly studies black holes that you can detect with LIGO, and in particular, the mystery behind why some of these black holes are very massive, and what this tells us about our universe and massive stars. She received both the Sierra and an Einstein Fellowship and is currently working at Northwestern, and she'll for sure tell us more about her work. So yeah, go ahead, Maya, and start presentation.
Great. Yeah, thanks so much for the invitation. And I'm really looking forward to having a conversation with all of you. So I'll just share my screen. Hopefully everyone can see that now. Great. Yeah, so today I'll be focusing on one aspect of the many lessons we've learned from LIGO and Virgo so far, and that's this mystery of the biggest black holes that Flor mentioned. So just for a very quick introduction, we have these several gravitational wave observatories. The ones that have been taking data so far are the two LIGO detectors in the United States and the Virgo detector, the French-Italian detector. There's also the Japanese detector Kagra, which will be coming online soon. It was supposed to join for the third observing run, which ended around a year ago. But because of the pandemic, things kind of got a little off schedule. And then there's also LIGO India, which should be joining the network in a few years. So far from these gravitational wave detectors, we've detected gravitational waves from around 50 mergers. And the latest set of detections is published in this second gravitational wave transient catalog, or GWTC2. And there were several papers that came out last fall summarizing these detections. So there's the catalog paper, the population paper, and the tests of general relativity paper. The one I led is the populations paper. And so a lot of the science I'll be talking to you about is in this paper. And there's a lot in this paper that I won't talk about, but I'm happy to if anyone has questions. So this is just a nice visual that my colleague Zohair Doctor made showing all of these events. We detect the gravitational waves from all of them, but we infer the masses of the two black holes and sometimes neutron stars as they inspiral and merge. And so for each of the gravitational wave signals we detect, the gravitational wave signal tells us something about the properties of that system. So for black holes, they're pretty simple. They can be entirely described by their masses and their spins. And so from the gravitational wave signal, we learn something about the masses of the two black holes. The primary mass, M1, is just convention that it's the bigger of the two. We learn about the spins of the black holes. There's a spin magnitude, which says how fast they're spinning, but also some direction relative to the other black hole and relative to the orbital angular momentum. And then we learn about the distance of the source from the detectors. That depends on the luminosity distance, and then some information about the position on the sky and the inclination and the polarization. And measuring these parameters for each event is known as parameter estimation. Just very briefly, what we show for parameter estimation results is a posterior, which by Bayes' theorem is related to the likelihood of getting that gravitational wave data stream in our detectors, given the source properties. Here I'm just saying masses times some prior. And the prior we use in the catalog paper, for example, is just flat in the detector frame masses. So this is just an example plot from that catalog paper that shows the analysis of every event individually. These are just the new events from the third observing run. And here it's showing the 90% posterior probability contours in total mass and mass ratio. And you can see that some of these events are labeled. These are the ones that are special. They had special, most of them had special papers that to go along with them, like single event papers before the catalog release, like GW 190521, which I'll talk about later, is by far the most massive one. There are also some 190425 is likely a binary neutron star system. 190412 has very unequal masses. The mass ratio is bounded away from 1, and 190814 is even more unequal masses and has a secondary object potentially in the lower mass gap. So all of these events are very interesting on their own. Back when we detected only like 2 events in an observing run, we were very careful about every event and we loved each one individually. Now we have so many events, we can't even really remember all of their names. But that's really exciting because we can analyze them as a population, and there's a lot to be learned from this population science. So what we do is now, rather than focusing on the individual masses of the black holes, we can introduce these population level hyperparameters that describe the distributions of the masses and spins and redshifts of all of the events. So as the most simple example that within LIGO and Virgo we've been doing since the first observing run is just fitting a power law model to the mass distribution of black holes, where now there's some probability of seeing a mass, and that depends on the power law slope. And now rather than being interested in what the masses of the individual black holes are, we're interested in the value of this power law slope alpha. And when we do this, we have to take into account measurement uncertainty and selection effects. So it's a little bit tricky. I've written down the likelihood here, and I won't go too much into it, but feel free to ask me more detailed questions about the analysis method. So here I've just listed all of the astrophysical lessons in the gravitational wave data that we have in this populations paper, which you can find here. So you can see we're starting to learn a lot about the masses, the spins, and the merger rate, and its evolution with redshift. But for this talk, I'll just be focusing on this first point, which is about the black hole mass spectrum and what happens above 45 solar masses. So I'll try to answer these 3 questions for the rest of the talk, but I just wanted to pause and see if there are any questions so far about the introduction.
Maybe we should also, maybe we should keep going and sort of discuss when we get to a little further.
Okay, sounds good. Yeah, so for the first point is where are LIGO's big black holes? And this was a paper that I wrote with my PhD advisor, Daniel Holtz, in back in 2017, just looking at the first 4 detections from LIGO and Virgo. We noticed that there was something weird going on in that the bigger the black holes you have, the more sensitive our detectors are to them. But all of the black holes we observed in the first 2 observing runs were down here below around 40 solar masses an individual. This is showing the total mass, so below around 80 solar masses. And then we didn't detect any black holes bigger than that, even though the sensitivity of our detectors increases. So we did this population analysis, and we found that these systems must actually be rare in the underlying population if the gravitational wave signals from them should be so loud, but we don't have any in our data. Maybe they're just absent in the universe. And so we did this fit to the black hole masses we observed. We fit a power law with sharp cutoffs at low mass and high mass. And we found that this maximum mass, where the mass distribution cuts off, was around 40 solar masses. And the data was consistent with coming from this distribution. And so so this is showing like that posterior on the maximum mass parameter. And you can see that we measured it to be 42 solar masses plus 15 minus 5.7. And this is just compared to the masses, the individual posteriors with those uninformative priors of the masses of the other black holes. And so you can kind of see like where this measurement is coming from. All of the black holes we've observed are consistent with having mass below this maximum mass, even though some of them with the uninformative priors might have support at higher masses, but that we argued that that is just a statistical fluctuation, that this is really the maximum mass of the black holes is somewhere within this posterior in the dashed blue. So in the next part of the talk, I'll describe what this means and how the latest discoveries of big black holes fit into it. Are there any questions on the first part? Okay. So this was a really interesting observational finding, because this was entirely consistent with theoretical predictions that have been going back to the 1960s about stellar evolution. And in particular, there's this prediction that when you have stellar cores that are in the range 40 to 120 solar masses, that star undergoes what's called a pulsational or just a pair-instability supernova and leaves behind either no black hole remnant at all, or has these really violent pulses where it sheds enough mass so that the final black hole remnant is below this 40 solar mass cutoff or so. So this was a pretty firm theoretical prediction for stellar evolution that would just apply to any black holes that are formed from stellar collapse. Of course, if you have a black hole that's not formed from stellar collapse, there's no need for it to obey this mass gap. You could have black holes that are formed from smaller black holes. They can be in the mass gap, no problem. And so this opens up this cool new science that we can do with gravitational wave observations, because clearly our observations are telling us something about the pair-instability mass gap, and what we measure of the black hole masses can help us resolve some theoretical uncertainties about pair-instability. So one example is uncertain nuclear physics. The location of this mass gap depends on most primarily Rob Farmer found in this paper, this one particular nuclear reaction rate. And so if you vary the value of this nuclear reaction rate by a couple of standard deviations, you can vary where the mass gap starts and also where it ends. There have also been a series of papers by Juna Kroon, Sam McDermott, and Jeremy Sackstein that talk about how beyond standard model physics can also vary where this mass gap is. And so the black hole masses that we detect with gravitational waves can also probe this beyond standard model physics. And so that was all very nice, a very clean picture from the first 2 observing runs. But then in September, the LIGO and Virgo collaboration, we announced that there was this new detection, GW190521, and this was very popular with the press because it's this like giant black hole. The primary was around 85 solar masses, and it's also exactly contradicts what we thought was true, which is that there's this mass gap there. So what is this black hole doing there? And so just for context, this is similar to that plot I showed earlier, where in the blue dashed lines, we have the maximum mass that we measured from the first catalog. And that was this number that was around 40 solar masses. This was the most massive event from that first catalog. And now we have GW190521, the primary mass is here in orange and the secondary mass in green. You can see that the secondary mass has some overlap with this maximum mass posterior. So, okay, like maybe the secondary mass is 40 solar masses and it's below the gap, but the primary mass has no overlap with this maximum mass. So it is inconsistent with our inference from before. And that is what makes it so surprising observationally, based on our previous observations and also based on theory. And so just very quickly, I wanted to mention this other fun interpretation from what might be going on is that actually, since what we measure in the previous slide, I showed the posteriors on the 2 component masses, what we actually measure well is the total mass. Like our inference on the primary mass and the secondary mass are very correlated. And you can see that in the purple here is just the 2D posterior on primary and secondary mass. And that means that if we actually assume that the secondary mass is below the gap, we say, well, it's probably more likely that that this system contains a black hole like the previous black holes we've seen, rather than 2 brand new black holes. So we move that black hole below the gap with a different choice of prior, then the primary mass actually gets shifted to have considerable support above the gap. So that is just one possibility. It's hard to tell to just play these prior games with one event, but definitely on a population level, we can start to see whether there really is a population of black holes above the gap. So that'll be exciting. I'll skip this slide for now. But it's not just GW190521. There are other big black holes in the second gravitational wave catalog that are bigger than anything we saw in the first 2 observing runs. So again, here in blue, this is that maximum mass that we measured from the first 2 observing runs, around 40 solar masses. And in these dashed and dotted lines, here you can see some of the primary masses that we've observed in the 3rd observing run that are pretty in tension with this maximum mass that we thought was true. And so if we now measure what the maximum mass is with the 3rd observing run, we get this red curve here. Even if we take out 190521, we get this green one here. So the maximum mass definitely seems to be increasing now that we have new detections. And so this kind of brings up a lot of questions. There are several possible interpretations. One is that maybe these more massive black holes that we've now observed in the 3rd observing run are inside the mass gap. The mass gap actually starts at 40 solar masses. These black holes are bigger than 40 solar masses. Maybe they're made in a different formation channels, like they're made from smaller black holes through hierarchical mergers or something else. Maybe the mass gap starts at higher masses than previously thought. And maybe the reason we thought there was a cutoff at 40 is no, there's actually not a cutoff at 40. It's a taper that starts at 40. And there's some rate of black holes above that taper, but it's just smaller. And that's why we're only seeing them now, is that there aren't as many of them out there. And another interpretation maybe is that there is a subpopulation of black holes above 40, but that evolves with redshift. So either there's a sharp cutoff that varies with redshift, or maybe these black holes are just found at higher redshifts. And that leads me to the last part, which is the evolution of black hole masses across cosmic time. And so this is just another way of looking at the black hole masses. We just add another dimension, and we see maybe this extra piece of information, the redshift, can help me disentangle these different possibilities for what's going on with these big black holes. And so here, this is these 90% probability contours. These are actually all, like, each one of these is a contour, even though they're all overlapping, of the primary mass versus the redshift. And what you can see is that in blue here, we have the ones from the first catalog, and in orange from the new events from the second catalog. And these new events that we've observed in the second catalog are actually probing higher redshifts, because the detectors became more sensitive in the third observing run. We're able to see black holes to farther distances. And so it makes sense we're looking at higher redshifts, but that's also where all of these biggest black holes are. So does this indicate that we're actually observing a different population, like the mass distribution is different at higher redshifts than it is at the low redshifts we were observing before? Or is it just that we're now probing a larger volume in the universe, and so we're able to see the rare events? And so this is from a recent paper that my collaborators and I put on the archive just last month. And we actually looked into doing this population analysis. So we assume that there's some mass distribution, either a truncated model, so that's just power law with a sharp cutoff, or a broken power law model, which allows for this more gradual taper at some break mass. And we allow these to evolve with redshift, and we fit for that. So here, this is showing the 99th percentile of the primary mass distribution as a function of redshift. And you can see that if we assume that the mass distribution has a sharp cutoff, this is this blue evolving truncated model, that cutoff must increase with redshift. And so the most massive black holes must become more massive at earlier times in the universe than today. But if there is more of a taper in the mass distribution, like there is some break in the power law shown in orange here, and we allow that to evolve with redshift, there's some hints that yes, maybe it does, but it's definitely not as strong. And it's also definitely consistent with not evolving with redshift. So this is what I just said in words. And another way of looking at this is looking at the rate of mergers, both low mass mergers with primary masses below 45 solar masses, and the heavier mergers with primary masses above 45 solar masses, looking at that rate across redshift. And so you can see that if the mass distribution really does evolve with redshift, then it's possible that that's in orange here. It's possible that the rate of the most massive mergers is very low at redshift 0, but then increases to a few to a few mergers per cubic gigaparsecs per year as we go out in Redshift. But another thing that is cool is that we do have evidence, even if the mass distribution doesn't evolve with Redshift, that the overall rate evolves with Redshift. So if the mass distribution doesn't evolve, then the rate at all masses must evolve with Redshift. And that starts to tell us interesting things about like the time delay distribution and star formation rate. And another thing that I briefly mentioned, I just wanted to say that people are definitely looking into this, is that maybe there are multiple formation channels going on. So I just talked about looking at what the redshift information can tell us in more detail about the mass distribution and the history of the biggest black holes. But we can also look at spins to add more information. And so the spin distribution at the highest masses compared to the lowest masses might tell us if there really is a different formation channel going on. And the one primary way to do this is by looking at the spin magnitudes. So this is showing a plot from actually my first paper from grad school, where here in pink, you see the spin distribution that we expect to have for black holes that are formed from earlier mergers. And there has been a lot of theoretical work recently too that suggests that maybe black holes born from stellar collapse are actually very slowly spinning. So that would be 0 on this plot. So seeing if the black holes that are bigger, maybe within this mass gap, tend to also be spinning at around 70% of the maximum spin, that could help disentangle these different channels too. And I'm just showing there are other papers, but there's one paper by a grad student at Northwestern, Chase Kimball, that was posted recently that looks at this analysis also. Okay, so this is my last slide, and then hopefully we can have some discussion. So just summarizing, I talked about where are LIGO's big black holes and the first evidence for this mass gap in the black hole mass spectrum. And then talking about some of the theoretical interpretations from that and the latest discoveries of big black holes, which are inconsistent with a sharp cutoff in the mass distribution. Maybe we've even observed a black hole on the far side of the mass gap. And then I talked about looking at the black hole mass distribution and its evolution with cosmic time. Maybe that can tell us something about the underlying physics of what's forming these big black holes. And then just to say that the how and why of this is looking at this provides clues about how the black holes are actually made. There's still some feature in the mass distribution at 40 solar masses, so we can't just like throw away the theory, stellar evolution theory that predicted this pair-instability mass gap. It's definitely still something going on in the mass distribution. It's just more complicated than we thought from the first 10 detections. And so connecting this back to supernova theory will help us say something about uncertain nuclear physics, maybe particle physics. And also there's a cool application that we can use this feature in the mass distribution to measure cosmological parameters, which I didn't go into, but I'm happy to if anyone has questions about that.
Wonderful. Thank you so much.
Yeah, thank you so much, Maya. I think this was a great talk. It's also interesting. I received a lot of questions, so thanks everyone, and feel free to still post questions to me. And I'm really happy, or it's very interesting to see that a lot of them are actually also about these redshift and cosmology. So, and since that's also a topic that you discuss a lot, I think that's great, especially since we have so many people here that are interested in the cosmological distributions. So actually, I think I want to first ask Jesse Hun to maybe unmute and ask his question, because I think it's kind of a good first question to start with. Yeah. Thank you.
Well, I got sniped. Thanks so much for the talk, Maya. That was great. My question was, what is the LIGO selection function when it comes to plotting the primary mass versus redshift, and how are you modeling the likelihood? Like, is it a Poisson point process? What kind of modeling is going on here?
Oh,
Maya, I think you're.
Yes.
Oh, yeah, sorry. Classic. Right. So we actually, so this is kind of a rough idea of what that selection looks like. This shaded region here are the systems that would be below this simple calculation of a signal to noise ratio. What we actually do, so basically you can see like at low masses, we can only observe them out to like redshift 0.2, and at the largest masses, we can see them out to like higher than redshift 1 in the third observing run. And then at even larger masses, they get the frequencies of the gravitational wave get redshifted. And so we start to lose sensitivity because they now merge outside of our band. And so what we actually do is we have injections. So we inject like the gravitational wave signal for given masses. We have like a broad distribution over masses, spins, and redshifts that we inject into data from the detectors and then run the search pipelines, which are the ones that pick out these signals to begin with. And then we look at the false alarm rate that the injections are found with and see if that's above threshold or below threshold. And then that goes into that second part is this, which I didn't explain at all, but great you asked about it. So we model, this is basically an inhomogeneous Poisson process likelihood, except the form I've showed here is marginalizing over the overall rate. And so these probabilities are just like this probability here is normalized over M1 and M2. If you integrate this over M1 and M2, it'll integrate to 1. So it doesn't have the overall rate in it, but basically this is the selection effect term which we have, which is the fraction of detectable systems in the population. And so just to very simply, if you have, this depends on like your population hyperparameter. So for very negative power law slopes, for example, there's now a much stronger preference in the population for low masses. And that means that this number will be smaller because I'll detect fewer systems out of that population. And so that serves to like upweight that value in the likelihood. And that's how we like account for those selection effects.
Cool, thanks.
Juliana, do you want to ask your question? I think that's a very, very interesting one.
Thank you. Yeah, thanks, Maya. This is great. So you kind of hinted at this in your conclusions slide, but do you think you could comment a little bit more on the stellar implications of these increase in mass gap with redshift? Is it expected because primordial stars are more massive? Is there something related to metallicity, or is there a more complicated picture going on?
Yeah, that's a really great question, and I don't know the answer to it. I like try to keep up with the literature, but I don't think there's consensus. So basically, we expect like the black hole mass distribution to depend on the metallicity of the stars that they formed from. So if anything, at higher redshifts, lower metallicities, we'd expect more massive black holes. But there's also, I think there are a lot of uncertainties about what the distribution of metallicities is at a given redshift. Like even at low redshifts, you have some pockets of the universe with very low metallicity. And this is further complicated because when we observe a black hole merger, we don't observe it at the redshift that it formed. There's some delay between the formation of the stars, which might be low metallicity, and then the formation of the black holes and the in-spiral and the merger. And so it could be that that time delay distribution is very broad. And so maybe some black holes that we observed at redshift 0 were actually formed at redshift 6. And so it's, in that respect, I think the theoretical predictions are complicated. And then another thing is, if we're actually looking at like the location of the pair-instability mass gap. So like there's like in these plots, so in Rob Farmer's paper about this called Mind the Gap, they did a calculation where they solved for where this mass gap is at different metallicities, and they found that the location of the mass gap was not very sensitive to the metallicity at all. Like it only varied by a few solar masses, because because the stellar winds did not really affect like the carbon oxygen core mass, and that was really what sets like where this mass gap is that carbon oxygen core. And so but then like they only evolved helium stars, like assuming that during binary evolution, everything in the star's life before it would have lost the hydrogen envelope. And then especially after GW 1905-21, that 85 solar mass black hole detection, there have been other papers that say like, no, you actually can hold on to the hydrogen envelope if you go to essentially 0 metallicity. So maybe like for population 3 stars, you can have the core be like below this mass gap range, but then you just have like 20 solar masses in hydrogen envelope that falls onto the black hole that can push it up. And so that would depend on metallicity. But yeah, I don't think there is consensus on that yet. Sorry for the very long answer.
No, this is great. Thank you so much.
Rainer, do you want to follow up on that, or?
I think I had more or less the same question, so I think that's about it. But I mean, generally, just what I would be interested in, and I'm totally not in working in this field, is, but do you have a clear sense of or ideas how to solve problems like your delay time or in-spiral time distribution and things like this, where this can be constrained in some crazy way at some point in the future?
Yeah, so I think we definitely, so I think like looking at the rate evolution, especially when we really start to be able to do that like within different mass bins, I think that will really clear up the picture. I mean, here I'm just showing like in 2 mass bins, low mass and high mass, for 2 different models, which look kind of very different. But eventually we'll have enough data where this will be a solved problem, right? Like we can just look at all of our 10 solar mass black holes and map out the rate, the astrophysical rate of those as a function of redshift. And then I think that will, like assuming that the time delay distribution doesn't depend too much on mass, I think that's a good assumption from like population synthesis papers that I've read, but I don't know if that's up for debate. But assuming that, then I think we'll really be able to go back to like, okay, then what is the formation rate of the progenitors to these systems as a function of redshift? And if it really is different for the 10 solar mass black holes, like if the 10 solar mass black holes, their merger rate increases in a different way with redshift than like the 30 solar mass black holes, then I think we'll be able to say that it really is dependent on the metallicity evolution, and kind of disentangle that. With the current generation of gravitational wave detectors, we won't really be able to probe much past redshift 1. Like we'll probably get to like 1.5. So we probably won't resolve the peak of the peak of the merger rate in like as a function of mass. We can learn more about the high redshift universe by analyzing the stochastic background. So I think there's like a limit to how much we'll be able to push this, but we're definitely not at that limit yet. We're definitely going to learn a lot more.
Yeah, I would actually follow up on that. And I think you already hinted to that, but so now LIGO has 50 detections, as you mentioned. And so I imagine that the current redshift distribution is still dependent on like the prior that you assume for how they're distributed. So do you have any idea like how many detections do you need to kind of converge on this, or?
Yeah, so I think we're actually converging really quickly on this. So I think now our number is like, I mean, what we do is we measure the slope of this redshift evolution, like it's 1 plus z to some slope. And we've constrained that slope to be like plus or minus 3 now, which translates to the merger. So this is if we assume that the mass distribution does not evolve with redshift, the rate is the same at all masses. We get that at redshift 1, the rate is like no more than 10 times higher than the rate at redshift 0. And it also doesn't like it's pretty much does evolve with redshift, but no more than like a factor of 10. With the second observing run, that number was like 1 million. So our uncertainty has already gone down by orders of magnitude. And that's really because like with the second observing run, we were only sensitive out to like redshift 0.5. So we now just have a much longer lever arm to like constrain that rate evolution. And yeah, so I think now we're at the point where like that uncertainty is just going to decrease with the number of detections, and depending on like where exactly it falls, that can definitely tell you things about like the star formation rate and the time delay distribution already. Like I guess for reference, the Maddow-Dickinson star formation rate increases by a factor of 6 between 0 and 1, and now we're like between 0 and 10. So we're kind of in that range. But if we if we say like the rate increases with redshift much faster than like the Maddow-Dickinson star formation rate, I think that will be really interesting. That definitely would say that like metallicity evolution has something to do with it.
Thanks. Morgan, do you want to follow up?
Absolutely, yeah. So I'm really interested in, and also like still a little bit confused by it, but only because of my not being able to like think through all the parts of it at once. So okay, so I'm sorry. So thinking about the like non-detection of very large black holes at lower redshifts. So is the as I understand the argument, basically if we fit one mass distribution to all redshifts, then we would, and the rate doesn't evolve with redshift, then we would expect to see them at low redshift. Is that correct?
Yeah. Yes.
At what point does the volume become too small, essentially, for the redshift that we're observing? Like in redshift 0.1.
Yeah, this is a really good question, and I think we have some plots in this paper to try to get this, because you're absolutely right. Right now, our conclusion is that we don't yet have enough data to say whether the absence of black holes, of the high mass black holes, so up here
right
at low redshifts, whether that is surprising or whether the volume is just too small. And so there is some tension, which is shown here between, like in orange is our observations, basically, and in blue is what we would have predicted. There are a lot more than 50 points here because it's showing like different draws from this, because we have uncertainty in our observations. But yeah, so right now we can't distinguish between those, which is why we can't really say like, is there really an absence? Like, is in the universe, are there really just no big black holes at low redshift? We can't say that yet, but we will be able to. So this is essentially taking that earlier plot and showing like the fraction of high mass detections at low redshifts compared to the fraction of high mass detections at high redshifts that we expect from like these two different possibilities. And on this side, you can see that right now with only 44 events in this analysis, this is why we can't really distinguish that, because the Poisson uncertainty is too big. So it's not surprising that we have seen pretty much zero high mass events at low redshifts, but the underlying predictions from the two are very different. So there's some prediction for just assuming, if you assume that there's this non-evolving broken power law, there's just a low rate of high mass mergers at all redshifts, then you definitely predict to detect like one of these high mass events at low redshift for every 3 high mass events at high redshifts. And so when we have like 10 high mass events at high redshifts, that like we would expect like 3 of those at low redshifts, and that becomes more significant when we have 20 at high redshifts. Then you basically win with the Poisson.
Yes. As we talk about like this generation of gravitational wave detectors and going from Z of 0 to 1.5, is essentially the time baseline constraining the lowest redshift end, like the small volume end? Is that going to be as much of a challenge as sort of pushing down into the noise on the high redshift end?
Yeah, so with the low with the low redshift end, it's mostly just time. I mean, as we do improve our sensitivity, but out to like redshift 0.1 or so, like very low redshift, where we can say like we're observing all of the black holes that merge. So that limit is just set by how many mergers are there. And the reason we're detecting so many more events overall is because our sensitivity is increasing at the highest redshift. So we're able to pick out more of those mergers out of the noise. But yeah, with like the planned third generation gravitational wave detectors, like the idea is that we'll be observing every single binary black hole merger in the universe. So I was going to say the only limit is how many of these mergers there are, but really there's also the limit of like how good our computers and our computational techniques are to analyze like hundreds of thousands of events annually.
Thanks.
Yeah, that's incredible. Another question that was put up was actually, what about the redshift dependent or redshift evolution of like mass ratio or the mass ratio of binary black holes, or otherwise other sources such as binary neutron stars?
Yeah, that is a great question. So this is really like, we've only taken the first 2 steps so far, which is looking at how the overall merger rate evolves with redshift, and then looking at how like the primary mass distribution evolves with redshift. We've also looked at how like whether there's some like mass ratio dependence with redshift, and the uncertainties were just really broad. But there's definitely, yeah, I mean, really like we would want to look at all of the properties, and we're kind of in the stage now where our simplest like parametric models are no longer a good description of the data. Like we used to just fit for one power law slope, and like clearly now that doesn't work. Like if we do that, then we have to also say that that value is different at different redshifts. So we're adding like just another parameter, and we're still just adding like a handful of parameters. Like you could add another parameter to describe, okay, how does the mass ratio distribution evolve with redshift? But then we realize like, oh, we can't really learn anything about that. So let's like take that parameter away. But yeah, like eventually this is just moving towards, we'll have thousands of these, and we can do a fully, like we'll just have the underlying distribution, and in some non-parametric way, we can see like which properties are changing with redshift, which properties are constant in redshift, are they co-evolving in some way that points at a specific formation channel as the likely one. So yeah, that's definitely going to get more interesting when we have more data.
Great, thanks so much. I'm also seeing that we're 4 minutes before noon, so, and I don't want to I want to give people some time before their next meeting. So unless there's any urgent questions, I'm gonna thank Maya again for her talk. So I'm gonna give her a virtual applause. Yeah, and Morgan, is there anything else?
Maya, any like last words on like what are you most excited about working on next? Like what are your vision for next steps that you're particularly excited about?
Yeah, so I definitely think that like some of the questions about, okay, what is this actually telling us about the star formation rate or like the metallicity evolution of the universe, I think those are really interesting, and I'm really like, I think thinking more about that, I'm really excited about that. I'm also really excited to like actually learn more about like other probes of of those things and like basically tie this gravitational wave data to other observations of the universe. So yeah, I would, if anyone wants to collaborate on things like that, I would love to step out of like the LIGO data analysis world for like a paper or two.
Amazing. Well, thank you so much. And thank you to everyone for the great discussion. And thank you especially to Flor for guiding us through. Yeah, thank you everyone, and we'll see you soon.
Thank you.
Thanks, everyone.